Hello everyone, welcome to lecture 35. Today we will talk about the remote sensing application in drought assessment or drought studies. In the previous lecture we have discussed about the basics of droughts. So before we continue this remote sensing application, we need to understand about the drought index. So let us see the few details about the drought index, what are their mathematical expressions and what parameter we require to calculate them, because drought index will be one of the parameter on which you will be able to decide whether a particular area is under the stress or whether it is having a severe drought condition. So you have seen these indices: percent to normal precipitation (PNP), standardized precipitation index (SPI), Palmer Drought Severity Index (PDSI), Surface Water Supply Index (SWSI), Reclamation Drought Index, and last one is the decile. This is the monthly drought, right. So, a drought index is typically a single number, but it is far more useful than the raw data for decision making, right. There are several indices that measures how much precipitation for a given period of time has deviated from the average precipitation, and this average precipitation can be derived through various methods. So, we call them historically identified. It is useful to evaluate one or more indices before making a decision. I mentioned this in the previous lecture also. If you consider using PNP or SPI or PDSI, SWSI, RDI or decile, all of them having their own limitations, right. So, to overcome this situation, we need to use at least 2 or 3 drought indices, so that the common area will be accurately identified and that we can confidently say this area is under the water stress, right. Here you can see this is for the PNP, and here the red one, this is basically your normal, and this is identified using this 1961 to 2010 precipitation data, right. So, for time being you can consider this as average precipitation. Now, you see the actual precipitation of this area between 1st June to 29th September of 2020 and how it is behaving, how it is changing, right. So, this you can consider, and this will help you to identify whether a particular area is having the stress or not, right. So, the PNP can be considered as ratio of actual to normal precipitation for a given location and period, expressed in percentage, analyzed for a specific region and season. Precipitation has different impact on the soil moisture, groundwater, reservoir storage, snow cover and stream flow, right. So, this PNP index depends on the selection of period, monthly, seasonal or annual. You can see here, this is 1st June to 29th September. Let us say this is 1st January to 31st December of 2020, right. So, for this you can have an average value, or you can have the monthly average value, or you can have the daily average value, right. So, anything can be considered here. So, it can be monthly, seasonal or annual, or you can divide them based on the seasons, right. SPI, a normalized index representing the probability of occurrence of an observed rainfall amount when compared with the historical rainfall data. It quantifies the precipitation deficit for multiple time scales. These time scales reflect the impact of drought on the availability of the various types of water resources. Soil moisture condition reflects short scale precipitation anomalies. because the soil moisture immediately will be an indicator which can say that in the last 5 days or 10 days precipitation has not happened. Whereas groundwater, surface water and reservoir storage reflects long term precipitation anomalies. If there is no precipitation in some area, then the groundwater will go low, surface water will be less and the reservoir storage will also be less. So, this is a long term anomaly or long term phenomena. The index value is negative for drought and positive for non-drought. We will see that. So, you can calculate the SPI using this equation, and here the usually SPI is calculated for 3, 6, 12, 24 and 48 months time period. The SPI is an index based on the precipitation records for a location and selected periods. It can be months or years. SPI values ranges between +2 to -2, and here you can see this 2 or high, that indicates extremely wet, and -2 and less extremely dry. So, if we are getting this situation, this is the extreme period of drought. So, from here onwards you will have the drought condition. Then comes the PDSI, Palmer Drought Severity Index. It is used to identify a meteorological drought. Remember, this is for the meteorological drought. Allows to compare between locations and durations. PDSI provides standardized measurement of moisture condition. So, this will be based on the moisture condition of the soil. It is based on the supply and demand concept and the water balance equation, taking into account the precipitation deficit, right. So, PDSI is calculated using precipitation, temperature and local available water content AWC of the soil, and here the values ranges between +4 to -4 or less. So, here you can see this 0.49 to -0.49, that is near normal. Now, from here onwards situation is towards the drought, right, and this is the extreme drought condition, this, right. Evapotranspiration, soil moisture, recharge condition, surface runoff and moisture loss from the surface layer are considered in this particular index. Long term trends are not considered. Remember, this is the limitation. Human impacts on the water balance are not considered in PDSI, because we are following the water balance equation. In near real time, Palmer's index become a hydrological index referred to as the Palmer Hydrological Drought Index, PHDI. Now comes the SWSI. It can be calculated using here this equation, and the details are given here, right. So, what it says is, it indicates the surface water condition including snow cover, right. Incorporate both hydrological and climatological parameters. So, here both hydrological and climatological parameters are included. Remember always, used to compare different basins. SWSI value ranges between -4.2 to +4.2, and the required inputs to calculate this SWSI is snow cover, stream flow, precipitation and the reservoir storage. So, all these are used together in SWSI. Now, we have the RDI, Reclamation Drought Index, and the expression is given here. So, it defines the drought severity and duration for predicting a drought, beginning and end of the drought, right. It incorporates the precipitation, snow cover, stream flow and reservoir level data, and here the value ranges between +4 to -4, and this is the extremely wet and this is the extremely drought condition, right. So, from here you can have the drought condition. Then comes the monthly drought, that is decile. In the first step of this decile, arrange all the historic average monthly rainfall data for a particular month and for a specific location from lowest to highest. Now, here you have to sort the data. Then divide them into 10 equal parts. Each of these equal parts are known as a decile. Remember, you have historical average monthly rainfall data, right, and then sort it lowest to highest, right, and then divide them into 10 equal parts. The first decile is the rainfall amount not exceeded by the lowest 10% of the precipitation occurrence. The first part, that will be the lowest 10%, right. The second decile is the precipitation amount not exceeded by the lowest 20% of the occurrence. These decile continue until the rainfall amount identified by the 10th decile is the largest precipitation amount within the long term record. Now, this will be the 100% and this is 90%, 90 to 100, right. So, here the deciles are grouped into 5 classes. Decile 1 to 2, that is lowest 20%, much below normal. Decile 3 to 4, that is next lowest 20%, here 20, then 20, this is will become the 40%, right, and this is below normal. Decile 5 to 6, middle 20%, near normal. Decile 7 to 8, that is next 20% and this is above normal, right. Decile 8 to 10, highest 20%, much above normal. So, this is how we are going to interpret our deciles. So, for example, if a month's rainfall February 2018 for a particular area is in the first lowest decile, then its total is less than 90% of the February rainfall totals for that particular area. I hope this is clear. If a monthly rainfall for a particular month of a year for a particular area is falling in the first decile is the first 10%, then its total is less than 90% of the total rainfall occurred in that particular month. If the monthly rainfall total is in the bottom of 3 deciles, then rainfall has much below normal and drought may be possible. If the 3 monthly rainfall total is in the bottom 3 decile, then drought conditions are probably evident. So, like that we have to prepare this kind of spatial map using the remote sensing and GIS, and here you can see different colors are representing different deciles, right, and these can be clearly identified whether a particular area belongs to which class, right. So, for this particular color it is this low or lower ones in 3 to 5 years. Then comes the crop moisture index, identifies potential agriculture drought, uses a meteorological approach to monitor week to week crop condition, designed to evaluate short term moisture condition across major crop producing region, because this moisture condition is very important in the initial phase of the cropping, right. Based on the mean temperature, total precipitation for each week and CMI value from the previous week for a specific region. Responds rapidly to changing condition, it is weighted by location and time, and it is used to compare moisture condition at different location, because you can perform the same analysis for 2 or 3 different location and you can compare. Used to describe the flow of water in and out of a system, for example, column of soil and drainage basin. It also involves organism including plant and vegetation, which helps to maintain water in dry or hot condition. general water balance equation which is being used here. So, this is P is equal to Q plus ET plus delta S, and here the precipitation, runoff and the evapotranspiration and the change in the storage are used together, right. So, this change in the storage we can easily calculate. So, that will be delta S, that will be equal to the inflow minus outflow. If we have this, then we can use this equation in different way, we can modify as required and we can evaluate the water condition in our area. It is very useful in evaluating the components of the hydrological cycle, snow melt simulations, climate change impact assessment, flow forecasting and agriculture water management. This has a wide application in water resource engineering as well as in the drought assessment. Now comes the intensity, duration, frequency. So, the relationship between drought intensity, duration and frequency can be studied with conceptual model. It deals with meteorological drought lasting for at least 1 year. The climate types are defined in terms of the ratio of mean annual precipitation PMA, remember this, and to global terrestrial precipitation PAG, right. So, this is annual global terrestrial precipitation, and the ratio of annual potential evapotranspiration EAP to the mean annual precipitation PMA. So, from where you will get, I have a table for you that you will be referring for the values. To complete the description, the length of rainy season is also indicated. For any year with precipitation P, drought intensity is defined as the ratio of deficit. So, the deficit will be calculated using this PMA minus P to the mean annual precipitation. So, this is PMA, right. For drought event longer than 1 year, intensity is the summation of the annual intensity, right. So, here this is the table from where you can identify the values, and here hyper-arid, arid, semi-arid, subhumid, humid, hyperhumid it is given, and the return period is also given here, right. So, you have to check all these elements and then you have to choose the value appropriately. So, when we talk about the drought assessment, so what are the parameters that are required to study or to identify whether a region is vulnerable to drought or whether it is under the water stress? So, we need to have these parameters. First thing is the temperature, then we have radiation, then we have wind speed and then relative humidity. And if you just try to understand why we are using these 4 parameters here, because the temperature, radiation, wind speed and relative humidity, all of them are having the direct or indirect impact from the scarcity of the water, right. So, when we use them together, we can calculate the potential evaporation and then we can also calculate evapotranspiration. Then we have the meteorological drought criteria. So, this is and the level of moisture, soil moisture, surface water, groundwater storage before drought. So, all of them will together go into this, and then we can identify soil moisture drought, and then further we can study the hydrological drought, right. So, this flow chart is one of the methodology by which you can study the hydrological drought. However, multiples of flow chart or the methodologies are available in published literature that you can follow. So, let us understand this drought indices and the parameter. So, the parameter that we have discussed in the previous slide, those are the indicator, right. So, how these two are different from each other? So, indices versus indicator, right. So, indicators are specific variables like precipitation, temperature, stream flow, groundwater level, soil moisture and snowpack that describes the drought condition, right. So, these are the indicator. but indices are numerical representation derived from indicators to assess drought severity over a specific time period. Now, you need to remember this, what is indicator, what is indices, right. So, our index is based on the indicators and we have some numerical values. Based on the numerical values, we can say that this particular area is under the drought or whether this area is under the flood, right, or it is in the normal condition. But the indicators are just simply the indicating factors or the parameters which indicate there is a chances of water scarcity, right. Indices simplify complex climatic data and serve as useful tool for communication with diverse users. Monitoring at various time scale helps identify short term wet period within long term drought and vice versa. So, let us say there is a 10 years of the drought period, right, but in between there might be a possibility there is a rainfall, and if we evaluate this particular time individually, this will not qualify the drought condition, right. So, indices help to quantify the severity, location, timing and the duration of drought events. Severity refers to how much an index deviates from normal condition with set thresholds making drought onset and end. Location defines the geographic area affected, while timing and duration determine when a drought starts and ends. The impact of drought depends on its interaction with exposed elements like agriculture, water supplies and human population. I hope you have understood the basic concept behind this drought assessment, and you might be having an idea how difficult it is to analyze or assess the drought situation for a large areal extent, right. So, in such situation, remote sensing proved to be an important tool providing you the information about the large areal extent. So, the drought monitoring is a complex phenomena due to its spatio-temporal variability and severity. Traditional methods rely on climate based indicators like the standardized precipitation index and Palmer drought severity index PDSI. So, these indicators are effective, but have limitations in capturing local scale drought variation, right. Improved drought monitoring approaches are needed for early warning system and proactive drought planning. So, with this, remote sensing comes into the picture, that we will be covering in the next part of this lecture 35. Thank you very much.